We are ready to prove that the dilations scale distances in a nice way. Recall that on Heisenberg group H1, we defined dilation by factor R positive by multiplying the first two components in R and the last component in R squared. Notice that as a map from R3 to R3, this is very simple. It's just a linear map, a multiplication by this matrix, and in particular its derivative, if we view it as a function from manifold R3 to itself, its derivative is just itself. And this will play a role later on. The first lemma toward proving our desired result is the following. If you have a vector which belongs to a horizontal plane at a certain point, then scaling of the vector, the homogeneous scaling we have introduced, gives a vector that belongs to the horizontal plane in the dilation of the base point. So if we dilate the vector and the base point, the horizontality is preserved. The proof of this cannot be really difficult. After all, it's just calculation. Recall that the if and only if condition for being horizontal for v at the point xyt was that c be 2ay minus 2bx. So we have this in hand by the assumption. And now we test to see if this new vector belongs to the horizontal plane at this new base point. And so we have to check the new condition. So the new c is r squared c. And we want to check whether that is equal to 2 times a, 2 times ra, the vector, times y, which is ry in this case, minus 2 times b of the vector, that is the second component of the vector, times x, the first component down here. And then we see that this is r squared, r 2ay minus 2bx, and then from assumption we had that this was equal to c, and that checks. So this means that if we call this, say, v tilde belongs to the horizontal plane at this new point. A consequence of this lemma is that if we have horizontal curves and we compose them with this dilation, we still have a horizontal curve. If delta at t is written as xt, yt, and so maybe t is not the right parameter, tau, and t at tau is horizontal. So it's just to fix some notation. Then delta r composed with gamma is the curve given by r times x tau, r times y tau, and then r squared times t tau. Its derivative, so the curve delta r composed with gamma derivative at tau, is r times x prime at tau, r times y prime at tau, and then r squared t prime at tau. And this is delta r applied to gamma prime at tau by definition. Okay, now we know that almost everywhere, to be precise, at almost every tau, gamma prime of tau belongs to the horizontal plane at gamma of tau. Okay, that's the notation for horizontal plane at a point, HP, H1. So we know that this is true by assumption, and so by lemma, by lemma at every such tau, the dilation of the curve's velocity again belongs to the horizontal plane at the dilation of the base point. So if we interpret it correctly, we see that this means that delta r composed with gamma prime of tau, which is this expression here, belongs to the horizontal plane at, well, gamma prime was horizontal at gamma t. The lemma says that dilation belongs to the horizontal plane at dilation. So delta r applied to gamma of tau, which is delta r composed with gamma at tau. So if we, I'm using a new color, if we think of this composition, if we think of delta r composed with this as eta, as a new curve, so we have shown that eta prime tau is in horizontal plane at eta of tau at almost every tau, which is exactly saying that eta curve is horizontal. So delta r composed with gamma is a horizontal curve, ending the proof that delta r preserves horizontal curves. With this corollary, now we can prove that dilation scales distances by a factor of r. Proof: we have to go back to the definition. By definition, for every epsilon positive, there exists some horizontal curve from P to Q with its length, so length of this gamma, because DCC is as infimum, so that means if we help DCC of PQ by only epsilon much, there is a curve satisfying this. So for every epsilon, such a curve exists. So what is this LG length of a gamma? So if gamma prime of t is equal to A, B, and C, and it's horizontal, then the inner product G that assigns a norm to this curve is A squared plus B squared, hence ignoring the part C, which is, by the way, uniquely determined by A and B by the fact that it is horizontal. So this was how we computed the LG length of a curve by integrating this quantity. Okay, so that's just a quick recall. So by lemma above, delta r composed with gamma is a horizontal curve, and obviously its endpoints are delta rp, so horizontal curve from delta rp to delta rq. And so again, by definition of the Carnot Caratheodory distance, DCC of delta rp and delta rq, which is infimum over all horizontal curves, will be less than or equal to the LG length of this curve. This is one particular curve, so it's always bigger than the infimum. But now here is again back to this notion that delta r of gamma whatever gamma prime is, A, B, and C, delta R composed with gamma, its derivative at t, is just RA, RB, and RC. Therefore, this length that we had, which was a squared plus b squared, is exactly scaled by r. Sorry, this is r squared, but it doesn't come into this calculation of rg. So therefore, the integral we will write will be exactly r times the integral that we write for Lg of original gamma. And now we had chosen this so that it's less than r times dcc of pq plus epsilon. So we found one particular curve connecting delta rp to delta rq with this property. But epsilon was arbitrary. That means, so since epsilon was arbitrary, this shows that dcc of delta rp and delta rq is less than or equal to r times dcc of p and q. Okay, now, do we need to prove the reverse inequality? Of course, but without much work. Because if we apply the same argument, with roles reversed, so that means we start with a curve that connects p tilde delta rp to q tilde. So reversed means we take these to be the starting points, and then we take delta of 1 over r, because then delta 1 over r of p tilde becomes p. We show that dcc of p and q, that is after applying this delta to p tilde and q tilde. So I'm literally looking up here and copying down here. So this will be less than, and r is 1 over r, and dcc of the points that we start with, which are p tilde and q tilde. So that will be delta rp and delta rq. But look, if you multiply by r, we end up proving equality. So this star and this double star prove that. So from star and double star, we get that dcc of delta rp delta rq is exactly equal to r times dcc of pq. End of this lemma. So this lemma is just not nice. It has important consequences. I believe that from this we can prove that the Hausdorff dimension of the Heisenberg group is 4, and a few other properties just from this scaling knowledge. And such videos will come soon as well. But let me know if you have any questions about these lemmas, and if you could see a faster way to proving this scaling fact. Until then, have a great day.